हेलो हेलो हेलो
बोलिए सुनाई दे रहा
गुड मॉर्निंग एंड वेलकम टू ऑल
पूछिए मैं ऑडिबल
आई डॉक्टर यादव कृष्ण कुमार working as assistant in department of industrial production engineering IRT Paragraphs. Today is the second session of one week faculty development program organized by Department of Electronics Engineering, Institute of Engineering and Rural Technology, Prayagraj. It's my esteemed pleasure to introduce and welcome Dr. Vivekanand Mishra. Dr. Mishra is working as a professor in Department of Physics at Alliance University, Bangalore. He did his Doctor of Philosophy from I.I.T. BSU in 2001. His area of interest are optical fiber communication system, DWDM optical network, broadband wireless communication system, mobile and infrared network. Dr. Mishra is having more than 20 years in teaching experience at UG and PG levels. He published more than 100 papers in reputed journals and 63 in conference. He guided 8 PhD students and 35 MTech theses in the field of electronics engineering. He has written the 2 books in the John Wiley and 4 books in the books chapter in tech publications. He also have a patent. He also completed 8 sponsored projects funded by the defense agency like E-Science Malaysian government, DRDO, and Department of Science and Technology. He worked as a professional membership like senior member of IEEE, fellow IET, alum IPA. I welcome once again Dr. Mishra for the today's session to share the experience, knowledge in the recent trend in electronics engineering. Thank you.
Good morning, everyone.
Good morning, sir.
Sir, thank you very much for your nice introduction.
Thank you, sir.
Okay, so there is some echo in the sound.
Okay.
that is not from my
Now, okay, sir?
Yeah, I think it's audible.
Yes, audible.
Yeah, yeah. Now it's okay. So
Okay.
now I will share my lecture. The
एक्चुअली वॉइस क्लियर है सबको
Okay, clear. Clear.
आप लोग बताओ गुड मॉर्निंग बताओ
Audio level is too low.
ठीक हो गया ऐसा नहीं
Okay, so it's visible, everyone? Sir, is visible? My
Yes, sir, it is visible here.
yeah,
I would like to
yeah.
request the participants, is it visible properly? I need a response from the participants, any of the participants. Okay, ma'am.
Yes,
Thank you.
sir. Yes, sir. It's visible.
Thank you, ma'am.
Okay, so very good morning to all of you. So the good morning to all of you. Okay, so sorry for slight delay because there was some network issue. So now I think all of you are able to see my slides clearly. Okay, so the topic what I have assigned to delivered is the design, formation, and characterization of optical fiber grating. You
Vivekanand,
know,
sir.
yes, sir.
Sir, please put it on the full screen, sir. Full screen mode.
I had
Uh,
put it the full screen, sir, but I will check.
सर इन लास्ट सर आप लास्ट में देखिए, लास्ट में 3 बना होगा कॉलम, जहाँ पे मैक्सिमाइज साइज करने का है, उसके थर्ड ऑप्शन पे क्लिक कर दीजिए सर एक बार।
Full screen.
Audio level is too low, sir.
The screen is full. In my it is not showing.
Sir, I have already did the full screen.
Okay, sir.
Then it's okay now, Nitin sir?
This is not showing on the full screen, sir. विवेकानंद विवेकानंद सर,
Yes, sir. I'm.
यहाँ
Yeah, tell
साइज
me.
मैक्सिमाइज होता है सर, उसके तीसरे ऑप्शन पे चले जाइए
Maximize
सर,
कहाँ करें? Size.
नीचे से देखिए,
Max.
डाउन साइड में है एकदम, ये प्लस और माइनस साइन बना हुआ है। Is it clearly visible to you all, sir? Respected ma'am.
Sir, it's visible, but please show. Keep it on slideshow, sir.
Okay, okay.
क्यों उसको Okay, so I think it's properly visible now. So let's we start. Yeah. Okay, so the topic of discussion is optical fiber grating. So before going to start the optical fiber grating, just to introduce about the fiber optics communication. As we know, fiber optics communication, one of the well established technology, and it's a lot of achievements which has been noticed in last few decades in the field of optical fiber communication. In fact, in 1970, after invention of the laser and glass fiber, the optical fiber communication come in very much in advanced field, because laser is, you know, one of the component which you use as an optical source in the optical fiber communication, have ability to emit the radiation in coherent. And if it will make coherency, then you know, then the information, the bandwidth is going to be the increase. So the main turn back which has been come in 1900 after 1960 invention of the laser in the, even if you're talking about the historical background, is a very long story history of the optical fiber communication. You know, in long age, in the people use the visible light to convey the information from one place to one community to other community, you know. And all 1880, Graham Bell was the first person who tried first time the information to be sent through photophone, but due to the lack of the components and all, is not success. So, but uh, after 1970, once the optical fiber communication has been started, still there was a problem of the attenuation. It was around 2000 decibel per kilometer attenuation was there in 1970 when the optical fiber communication has been first time introduced. But a lot of work has been done, and now today's scenario is the optical fiber communications, it's have only 0.01 decibel per kilometer. So this is one of the unique property of the optical fiber communication. This is the reason the copper wire communication has been replaced. Not only the attenuation, if you see the bandwidth, huge bandwidth only can offer from the optical fiber communication. Nowadays, people are claiming 10 gigabyte. Already his work is doing 10 gigabyte by using the WDM and DWM technology. Theoretically, people are claiming in terabyte. So if talking about 10 gigabyte information sending per second is a huge information. And you know, every 4 to 6 months, the bandwidth requirement is going to double. Everybody need to see the movie, want to play the game through the net. So who is going to fulfill that requirement? So only one option which we are able to see, that is optical fiber communication. Especially in 1990, the WDM and DWM technology which has been introduced, you know, then multiple channels, multiple wavelengths can be accommodated in the single fiber, is known as the WDM and DWM technology. And these multiple channels can be take huge information at the same time. All the telecommunication industries, you know, BSNL, Reliance, when they are introducing the 4G, 5G, what is this? This is in fact implementation of WDM and DWM technology, in fact. So suppose any telecommunication agency, they are providing maybe around 100 gigabyte information in the particular area in particular time. And at suppose after 6 months, after 1 year, the bandwidth requirement is going to double in that particular area. So what to do that? How to increase the bandwidth? So very good way is the WDM. In WDM and DWDM technology, no need to digging and again install the fiber is not required. Towards the source side and towards the receiver side, just receiver which already has been installed, you can convey the information is you know, in more than in 100 gigabytes. So what I'm trying to say is that optical fiber technology is the technology who is going to fulfill the requirement of bandwidth in the future. So if you're talking about optical fiber technology, so a lot of things are there which is connected with the optical fiber technology. For example, like what I discussed about the WDM and DWDM, like one of the very good technology which is part of the optical fiber communication. This is the solitons. You know, soliton is the one of the soliton technology where the information will maintain from the beginning to end. There is no any losses will take place. If it is like that, there is no loss of the information. You know, in the optical fiber communication, when the signal is transmit from one place to other place, so after 200 kilometer, after 300 kilometer, there is a dispersion will take place. Dispersion will take place. The spreading of pulse will take place, and due to that spreading, due to the overlapping of the pulses, a lot of information is going to be the loss. So who is going to maintain this? So it's of course a lot of components of we have, like we have optical amplifiers and regenerators who will again maintain the shape of the pulses, shape of the information, and again maintain the quality of the information. But if suppose the pulse who will carry the information from beginning to end without any dispersion, without any loss, this technology is known as the soliton technology. So soliton technology is one of the new technology which has been introduced recently, just in year 2000, and this technology have huge power to do a lot of work in the optical fiber communication. Okay, so if talking about the optical fiber communication, so of course so many passive and active components are there, and that active and passive components sometimes we have need to be control the light. Optical fiber communication means what? There is a laser who will convert the light signal to the optical signal, and that optical signal will convey the information through the by obeying the total internal reflection law in the optical fiber. And at the end, there is a detector as a photo detector who will convert that light signal to the electrical signal and then process further. So this is in fact what's happening in the optical fiber communication. The optical signal is responsible to carry the information from one place to other place. So it's very difficult. It's very difficult to control the light pulses. Very difficult to control the light pulses. Means if you want to routing, if you want to change the path of the particular signal which is coming, so how to do that? So of course so many big components are there, bulk optics is there, but higher losses is there. Okay, but for if you want a device who have ability to minimum loss, who have small in size, low in cost, and using that device can play with optical signal, then it will be very much easier in the optical communication system. So the one of the device which is very much useful, this is known as the fiber brake grating. Fiber brake grating, one of the component who have ability to control the light, who can give the routing of the light signal, you know, and who can reflect, who can refract, who can understand the spectral shaping of the light signal which is propagating, can work as a sensor. So many things we can do just by one of the component, one of the very tiny component, very less expensive component, which is known as the fiber brake grating. So fiber brake grating is one of the component which is the revolutions come in optical fiber communication due to the lower loss done into the fiber. It's easier to compatible with the fiber, easy shaping of the spectral response. So due to all region, the fiber brake grating is one of the components which is very much useful nowadays for the optical communication system to controlling the light, we can say directly. So now we'll see what is the fiber brake grating. Fiber brake grating is nothing but just periodic variation of the refractive index in the fiber is known as the fiber brake grating. Periodic variation, you can see in this figure. You can see in this figure here, this is the optical fiber, and you can see this blue color. There is a writing of periodic refractive index variation. You can see it's periodically there is a change of refractive index inside the core region. Yes, this is the core region, and this is clad region, and above that there is a, suppose there is a medium is air. So of course, every medium have different refractive index. So N0, N1, N2, N3. So N2 is the refractive index of the core, and N3 is the refractive index of the periods which has been written inside. So this is the way how fiber grating has been fabricated. So just writing, or we can say that periodic variation of refractive index inside the core, you can see here. So light is totally depend upon the refractive index of the material. The propagation of the light, the transmission of the light is depend upon the refractive index. So the refractive index of core is be greater than refractive index of the clad, then light will obey the total internal reflection law and light will not go out of the cladding region. But here you can see light which is coming in the core, again there is change of the refractive index. So of course light is going to be the interrupted. Light is going to be the interrupted. So at which way you want to be interrupt the light, you want to transmit the light, you want to reflect the light, we can design this grating period. The grating period play an important role. Based on that, how much strong this grating period, it will let you know that property of light, how going to be the change. So in this case, there's a core refractive index. You can see how the variation of the core refractive index, and N2 is the refractive index of the core, and N3 is the refractive index of the variation refractive index as a grating. So you can see when the spectral response, the input will be inserted inside the optical fiber, a fraction of light which has been reflected. You can see here, fraction of light which has been reflected, lambda b. This is known as the Bragg reflectance, lambda b. What does mean of that? This lambda b is equal to an effective period. Means the reflected light from the grating is totally depend upon the change of the refractive index difference between the core and the period, and how much is the length of the period. And n effective is the responsible for the reflection of this fraction of light, which is known as the lambda b, or we can say Bragg reflection. So this is one of the very good application of the fiber grating. Specific wavelength we can reflect according to the requirement. We can design the grating, and according to our requirement, we can design the grating and we can reflect the light signal. So this is one of the fundamental fiber grating working principle. In the fiber grating, the main modes which is going to be coupled, this is the fundamental modes, the modes which is only propagating in the core region. You can see here, light signal is coming here and get reflected, and after get reflection, they are coupling to each other, and this coupling will let you know what is the spectral response of the light. So here same modes are here, same only the modes which is propagating in the core region. So same modes is there. So that's why here the n effective is going to be combined together, and we can say the Bragg reflection is equal to n effective 1 plus n effective 2 into period, and Bragg reflection is coming to n effective period, because both modes here are identical. So Bragg reflections will be here 2n effective multiplied by the period between the two gratings. So this is the period. This is the period between two, and this is the first order, and only first order is not going to be the second order mode of the diffraction, only first order. Okay, and then it's going to be coupled together, and after coupling, how much strong coupling is there of the modes, it will let you know the spectral response of the output. Refractive index profile variation inside the fiber grating we can define with this formula, where you can see the core refractive index variation function and apodization function is the components which will let you know the spectral response of the grating. See, this is the spectral response for the fiber grating. So specific range of the light signal has been get reflected, and remaining has been transmitted further. Okay, so this is the property of the fiber grating. Now we'll see how to fabricate that fiber grating. So there is several way to fabricate that fiber grating. Internally we can write, or externally we can write the grating. So for internally write, we need to be understand about the photo sensitivity of the property of the photosensitivity of, because optical fiber is made from the silica atom, and we dop the germanium inside. We can dop the germanium inside and make some impurity, some changes, and that refractive index we can change, but just by doping of the multiple semiconductors materials inside, and based on that we can modulate the refractive index of the particular okay. So the changing of the internally if you want to change, if you want to write, then we need to be use the photosensitivity formula, photosensitivity method. You can see here, this is the optical fiber chemical compositions. Seems here silica dioxide, germanium doped inside as a defect, and that germanium silica bondings only we can break just by applying a 5.06 electron volt energy. And you know, if the breaking of the bonding means changing of the refractive index, and if continuous in the fiber, there is a if you apply 5.06 electron volt energy, and there is a continuous change of the refractive index will take place inside the optical fiber. You can see here in this figure, this is the Hell grating in optical fiber, how the single mode argon laser is here, and this is the lens. When light signal is coming inside the optical fiber, a standing wave will form inside, and that standing wave will form and creates permanent modulation of refractive index inside the fiber. And that's why this is the way how to get the change of the refractive index internally inside the fiber. Okay, so this is the internal. What about the externally? If you want to write, you want to make a grating. So there is several method. One of the method is holographic techniques. You can see here, ultraviolet lights has been splitted in two part, and then it will be interference will take place in the fiber. Here you can see this is the fiber, this is the source, this is the spectrum analyzer. So just by precisely moving of this ultraviolet signal up to down, and by making a interference, okay, we can change the refractive index inside the fiber. Okay, the theta between the UV is the one who will let you know how much grating period you are interested for. So theta will increase or decrease, will increase or decrease the periods in between the fiber. So this is one of the way to fabricate the grating in the fiber, where we can see in OSA, in optical spectrum analyzers, we can watch at the same time what are the changes will, and what is the grating length and all we can see from here, and according to that we can increase or decrease the theta value here, and we can make the grating inside the fiber. So this is one of the way to fabricate the grating inside the fiber. One of the technique which is very important is the face mask technique, where corrugated periods has been used, and when the ultraviolet light signal will incident, then there is interference will take place of the two. You can see the interference techniques. By the interference techniques, this is the corrugated grating, and light signal is incident from here, and photo imprinting will take place in the fiber here, and here two plus minus one diffraction pattern, first minus first order and plus first order diffraction pattern will decide what is the length of the periods will be going to be right inside the fiber. So this is one of the method very much useful to fabrication of the period inside the fiber. So this method is very much useful because it's very easy to align, and it's very less cost effective. Next method is also the point to point technique. Here precisely the fiber has been moved and the ultraviolet laser signal will incident. So this ultraviolet laser beam will incident point by point, and grating will write inside the fiber. So this is the fiber holder where fiber has been held inside, and precise monitoring from take place from this device. And this is the ultraviolet laser beam is coming from here, and lens imaging slits in the fiber. Light signal is coming and incident point by point, and it will be writing the grating inside the fiber. Or we can say there is a variation of the grating length, grating pitch. Spectroscopy can easily be incorporated in such method. Okay, so now we'll see what are the application of the fiber brag grating. So a lot of huge application, not only in the optical communication system, but some other application in medical system, in hospital, and all. Optical fiber grating is so much useful. First, we'll see what are the use of the fiber brag grating in the optical communication system. You can see this is one of the system which is showing the WDM technology. See here, this is the WDM technology. Multiple transmitters are here, and this is the multiplexer. So multiple low bandwidth signal going to be combined together and accommodate in the single fiber here. Accommodate in the single fiber. So very narrow spacing of the channels in between the fiber, and this is the booster who will increase the amplify the signal. And this is inline fiber. This is optical fiber. So once the light signal, multiple light signals are coming, so of course, due to the property of the dispersion, so dispersion will take place. And also we are able to get gain from the different pulses with different in count. So different pulse, different signals, different gain we are getting. That's why there is no flattering of the gain. No flattering of the gain. So we want to gain flattered. If gain will be flattered, then we can use that signal in more effective way. So GFF is the gain flattering filter who will make all the gain flattering to combine together, and then that flattering gain we can use for the amplification purpose, or for any other for signal enhance the or we can say that it will maintain all the information in all together. So this is the gain flattering filter, and this gain flattering filter is made from fiber brag grating. Fiber brag grating concept will be much more clear when I will explain you some other application of the grating. You see multiple signals coming here, and they are very narrow in spacing, in nanometer in spacing, less than nanometer in spacing, and each and every signals, the gain is not in flatter in nature. So making the flattering in nature, GFF this is the made from the fiber brag grating, and it will make all the signals flatter together. Then we can get at the end more effective way of output signal. So this is the gain flattening signal, one of the application of the fiber brag grating in the WDM system. So not only gain flattering in WDM, also it's very much useful gain flattering in ADFA, dispersion compensation, add drop multiplexing in WDM, fiber laser, sensor technology. These are the applications of the fiber brag grating, huge applications. So we know that one of the very important component in the fiber optic technology, this is the EDFA, erbium dot fiber amplifier. We know that erbium dot fiber amplifier is one type of the amplifier who will enhance the, or we can say it will maintain the shape just by getting the radiation by EDM materials. EDM material has been poured inside the fiber itself, and once the light will incident, then this EDM materials will get excited, and then emission of radiation will take place, and that emission of radiation is going to be the multiply with the signal which is coming, and that's why signal is going to be get strength. So one thing which is very good property of the EDFA is it will emit around 980 and 1540 nanometer of the signal, and that two signals are very much useful, especially for the transmission purpose. So EDFA also will emit in the same range, so that's why it will be going to be multiply with the incoming signal, and signal is going to be boosted. So this is the property of the EDFA. Okay, so but one of here you can see the EDFA bandwidth is 35 to 40 nanometer bandwidth. This is the gain what we are getting from the EDFA, 35 to 40 nanometer, which is a huge gain. But one of the drawback is the gain what we are getting from the EDFA, 35 to 40 nanometer, that gain is not flattened. So we have need to make the flattened for getting the more effective way in the signal. Okay, so then we need to use the fiber break grating. See here, everyone. Yeah. See, this blue color line. This is your gain pattern of the EDFA. Gain pattern of the EDFA. You can see it's not flattened. So if it is not flattened, then its intensity is going to be not so much higher. So we have need to get a flattened gain. So how to get this flattened gain? You can see for getting the flattened gain, just we have need to use the fiber break grating. And grating we can design who can give the output just opposite of this. See, this is the output of a grating. Okay, now both have to be combined together. Superposition. After superposition, you will get gain flatten in pink line. You can see here. Now this is more effective compare of the unflattened gain. Okay, and this one we can get just by applying the grating. Okay, so I told you in the beginning, we can design a grating. We can design a grating according to your requirement. You we have fabricated the grating in the lab, and we use according to our requirement. So our requirement is what? Which type output you are expecting? That depends upon your design system. How you are going to design the grating inside. We have designed the grating here who can give the output exactly same, or we can say exactly opposite what gain we are getting from the EDFA. See, this is the opposite, and then make a superposition to these two, getting the flattened EDFA. So this is one of the very good example application of fiber break grating in the EDFA, because nowadays all the long distance communication we use the EDFA for the boosting the information. Every 400 and 500 kilometer we use the EDFA in the optical fiber line to enhance the signal quality. And as all of you know that EDFA has just invented in 1990. Before the EDFA we have regenerator. And regenerator what do? Just will convert the light in the electrical and then amplify and then again convert to the light. So OEO, optical, electrical, optical, it was there. But after EDFA has invented in 1990, then just optical to optical we can amplify the signal. So this one happened after 1990. Now of course it's a bit expensive compare of the other OEO components, but it's very easy in optical communication system to enhance the signal every 400 and 500 kilometers. See, all C is with net of the optical fiber. There is a long connection of the 5,000 kilometer connection between the Singapore to the Mumbai, and inside the ocean optical net is there. Optical net is there, and every 400 kilometer there is an optical amplifier which has been installed. Excuse me. Okay, so that EDFA will boost the signal optical up every 300 and 400 kilometer. So this is the advantage of EDFA in the optical communication system, and that EDFA again we can flatten by the fiber break grating. Okay. Okay, next issue of optical communication system is the chromatic dispersion. There is a delay will take place arriving of the pulse at the output. You can see above than 400 kilometer, in the beginning, 3 colors pulse is there the same, but after 400 kilometer, they are arriving with different time. And if this is known as the delay difference, and if delay difference will take place, then information will not 100% accurate. Okay. Even you can see after 400 kilometer, in the optical fiber, you can see which is the pulses is coming like that, and is losing the shape. Now it's broadened, overlapping. So such problem will take place in the optical fiber communication system. So fiber break grating is one of the technologies who can minimize such type of the problem just by using a component known as dispersion compensation. See here, this is the grating. Now see, the grating spacing is increasing. Grating spacing is increasing. So this is the one of the type of the grating. Okay, so now multiple signal is coming, suppose in the grating, and suppose the longer wavelength have travel longer distance, and the shorter wavelength will travel the shorter distance. See here, lambda 4 is the longer wavelength. Okay, lambda 4 is the longer wavelength, and lambda 1 is the smallest wavelength. So longer wavelength have to be travel longer distance. See, longer wavelength have to travel longer distance, and shorter wavelength lambda 1 have to travel shorter distance. Okay, so what will happen? It will delayed. The longer wavelength will delayed and allowing to reach with a shorter wavelength at the output. So now shorter wavelength and longer wavelength, they both will reach at the output at the same time, just by slightly change in the grating spacing. Just by, I told you, we can design according to the requirement. So here is requirement is how to reach all the pulses at the output at the same time. So this is the way how to send all the wavelength at the output at the same time. So this one, by using such type of the grating, by making such type of the grating, okay, multiple signals can be accommodated, and according to the longer and smaller, they will travel longer and smaller distance, and there is delay will take place by the longer wavelength, and due to that delay, that longer wavelength will also reach at the output with a smaller wavelength, shorter wavelength. Okay, this is the way how to minimize the pulse delay by using the fiber break grating. So such type fiber is known as chirp fiber, chirp fiber break grating, where the grating period will increase. Okay, and if signals will come inside such type of the grating, then it will maintain the shape as beginning. Okay, so one of the another very good example application of the fiber break grating is the I.E.R.T drop. Optical I.E.R.T drop is when low bandwidth signals will combine together and then accommodate in the single fiber, and single fiber accommodate, and this is the I.E.R.T drop multiplexer. Here, according to the requirement, we can drop and can
Your voice is not sub.
transmit further, and then demultiplexer will demultiplex what wavelength you want to be removed from the system. That one we can decide from the I.E.R.T drop multiplexer. And how to make this one? This one we can play with very easily, just putting a grating here. Suppose we put a grating here, then what will happen? Suppose we make a grating whose wavelength, or we can say whose period is matching with this lambda 4. Then what will happen? This lambda 4 will get reflected. Okay, so this add drop multiplexer we can replace and make a fiber break grating here. And what wavelength you want to be reflect, what wavelength you want to be transmit, just design the period, and according to that period's design, multiple wavelength can be dropped, multiple wavelength can be added and can be processed further. So this is one of the application of the fiber break grating. We know that in optical fiber communication, optical cavity play a very important role in the laser. In the laser, optical cavity play a very important role. In fact, optical cavity is the one who make the light signal coherent. Only wavelength and the length of the cavity. If the length of the cavity and the wavelength is compatible, then light signal which will enter inside the cavity, that will maintain the coherency. And if it will be coherency, then it will be like a laser, because laser of the main principle is the coherent light source, and that coherency made from the cavity.
Voice break हो रही है.
So in the laser cavity, light will be resonant back and forth. Round trip distance will take place between two mirrors, and that 2 dn is equal to n lambda. D is the distance between the mirror, and lambda is the wavelength of the light. So if maintain this range, then we can get output a coherent wave in terms of the longitudinal and transmission wave. Longitudinal and transverse wave. So you can see this is the some steps of longitudinal wave which is coming output of the cavity. It is something like this. This is the emission lines in terms of the longitudinal wave. So multiple longitudinal waves is coming, means multi-modes are coming. But nowadays age is single frequency laser. We want only single mode, single output. So how to do that? This one also the way by using the grating. You can see here, this is the Bragg reflector. So if you design the Bragg reflector like that, that Bragg reflector only will allow the cavity, the radiation output will become only 980 nanometers, suppose, then it's known as single frequency laser. Why you choose 980? Because 918 is the one of the very much useful band where minimum loss will be there, and also EDFA will support for the 980 nanometer. That's why I choose the 980 nanometer. So if single frequency will be there, more bandwidth will be there, and more bandwidth will be there means more message carrying capacity will be there. So this is the way how to make a single frequency laser just by using the fiber Bragg grating. One of the very good example application of the fiber Bragg grating is the sensing technology. See, almost we have multiple sensors in the mechanical engineering, in the electronics engineering. Multiple sensors are there in the very low cost. We can sense the temperature, we can sense the pressure, we can sense the strain, stress, all we can sense. But if you use component which is related to the optical fiber component, optical fiber technology, then it will be much more useful, because optical fiber components if you're using, then that component is explosion proof. There is no short circuit, there is no cross connect, because they are electrically isolated. Okay, so sensing technology of such devices are very much useful because of the unique property of the non-electrical method operation. Nowadays we can see multiple sensor components what we have, due to the short circuit they got damaged. But if you use a sensor which is from the fiber optic technology, which is made from the optical fiber, then this problem will not take place. So this is the reason in the sensing technology, optics related materials are very much useful because of the explosion proof, because of the no cross connect, because of the no short circuit. Okay, so sensing technology is one of the very good field for the optical fiber communication, where we can use multiple components for a sensor. Here also we use fiber back grating as a sensor. We can see here, this is the input spectrum, and once the input spectrum is coming and pass through a grating, then you can see a slightly shift, induced shift will be there, which is known as the lambda b. And this shift will let you know the property of the material which we are sensing. How much shift is there? This shift will be different for different sensing materials. So this is one of the way how to use fiber back grating as a sensor. So here you can see such type can make the device, like this is the source, and light signal is coming, and this is the fiber back grating has been installed inside, and then it's reflected back fiber reflection we can monitor here, and you can see the induced shift. And that's we did the modeling of the fiber back grating. You can see here, this is the fiber back grating with length L, and E0 and EB, EA and EB, this is showing that signal is going and signal is coming. So when signal is going and coming, the electrical field, then we can write the fundamental equation of the electrical field, AZE I omega t plus beta z, and for the coming signal EB, we can write BZE I omega t minus beta z. So we know that omega and beta is the property of the optical signal, where showing the frequency, the propagation characteristics and all. So by this equation and by this way, we can the modeling of the fiber back grating, and after solving further, we are able to know, putting the boundary condition and all, we are able to know the scattering matrix. By using the scattering matrix, we can get the scattering components S11, S12, S21, S22. These are the scattering components, the light signal inside, and AL B0. This is the boundary condition. So by putting the boundary condition and scattering components and solving further, we can get what is the reflectivities property of signal inside the fiber back grating. Also, we can use the transfer matrix method. Transfer matrix for each and every period, T1, T2, T3, this is the periods are of any grating. For each and every period, we can use the transfer matrix method, and we can design just by using matrix formula, and by putting the boundary condition and all, we can get how much is the reflectivity. So this is for the single, this equation for the single period, and this is showing, suppose multiple optical elements are there, multiple series of periods are there, then you can use this formula, and we can proceed further solving this matrix, and we can get finally the reflectivity of the fiber back grating. And here you can see the reflectivity of the fiber of the grating length and wavelength is totally depend upon the coupling of the signal inside. Okay, so these are the properties of the fiber back grating, and these are the some result of the simulation which we have received for the fiber back grating. For the an effective, if you put 0.008 maximum reflectivities at 1155 nanometer, which is coming around 93.7%. 93.7%. This is the reflectivity of the fiber back grating. If you put length of the grating is 1 millimeter. 1 millimeter. Also, we can see here the reflectivity is not 100% because there is some side lobes, and we need to remove these side lobes to minimize the loss. And if you remove these side lobes just by apodize grating, Just by changing the geometry of the grating, we can minimize the side lobes. And if we minimize the side lobes, we can get sharper reflectivity. And the phenomena of minimizing the side lobes of the output of fiber brick grating, that period is known as apodization. So here you can see the multiple results are there for the fiber brick grating for different length. You can see for when the length is 0.5 millimeter, 1 millimeter, 2 millimeter, 10 millimeter, the length is increasing. Now see how the reflectivity or power, you can see how getting in different form. So one thing is clear that if length is increasing, then FWHM is going to be the increase. Full width maximum, half maximum is going to be increased. Here you can see the wavelength at 1500 and 50 nanometer, here also the same, but the FWMH is increasing. First thing. Second thing, also you can see that side lobes are increasing very fast. See, side lobes are increasing. That's why your intensity of the maximum reflectance is not so much sharper. So that side lobes we can minimize just by designing the geometry of the period inside the fiber brick grating. This is the maximum reflectivity for the fiber brick grating, which will be increased with increase of the length. You can see when the index difference is also, you can see it's 0.012, 0.003, then how the reflectivity percentage is increasing in the fiber brick grating. Here you can see the bandwidth. See all the things what we were talking about the bandwidth. We, of course, every time we are looking for larger bandwidth. So larger bandwidth is depend upon the FWMH. So you can see how the bandwidth reduces with increase of the length. See, length is increasing, so FWMH is decreasing. This is indication of the decreasing of the bandwidth. So length of the grating, the index, refractive index difference and effective, these all play important role if you want to design perfect fiber brick grating for the bandwidth. Then you have to keep in all these things mind for the higher bandwidth. Strength, you can see, as I told you, the lobes or side lobes play an important role to increase the strength of the grating. So the strength side lobes of the reflective curves increases with increase of the grating length. Also, okay, if you make a grating whose periods are increasing or decreasing in shape, you can see here in this figure, periods, the distance is decreasing here. From beginning to end is decreasing or increasing. So if you make a grating like that, it's known as chirp fiber brick grating. Chirp fiber brick grating. So for the chirp fiber brick grating, the output for different length, it is like that. See, for 1 millimeter, for 2 millimeter, for 3 millimeter, if the length is increasing of the grating, see, for 1 millimeter, this is the your output of the reflectance of the fiber brick grating. For 2 millimeter, 3 and 5 millimeter. So length is increasing, then also there is an effect of the side lobes. Side lobes are affecting, increasing. That's why the sharpness of the FWMH is going to be decreased. Sharpness of the reflectivity is going to be decreased. So length of the grating play an important role. Here, design of the different types of the fiber brick grating. We can design a fiber brick grating with no apodization in this form. We can design a fiber brick grating in zinc apodization. We can design a fiber brick grating in Gaussian apodization. Also, we can design the fiber brick grating with raised cosine apodization. These are the different way how we can design the fiber brick grating in the terms of the length, in the terms of the sharpness and all. We can design according to the requirement. And if we see what are the output of such type of the fiber brick grating, you can see here. See, for the no apodization, you can see sharp reflectivity is here, but side lobes are there. Side lobes are there. As you know, if more side lobes means your bandwidth is going to be minimum. Bandwidth is going to be minimum. So side lobes, we need to minimize that. So we can minimize just by designing the grating like sink apodization, Gaussian apodization, or raised cosine apodization. So you can see the raised cosine apodization, if you will design your grating like D, raised cosine apodization. See, your output is very sharper. There is no side lobes. In this case, the bandwidth of the signal will be larger. This is already we have published. Okay, so finish the first part of the discussion, which is the fiber break grating. Now, also we know that one of the very famous grating, which is the long period grating. Long period grating is the transmission grating, and the fiber break grating is the reflectance grating. So here we will see how does grating we can make a long period, and how does it will work as a sensor and all. With this thing, we are the things we need to be discuss here. First time fiber break grating, long period fiber break grating has been introduced by one of the very famous researcher, Wengsarker, in 1996. In fact, we did all the work based on his first paper, and that paper is explain all the things about the fiber long period gratings. You will see. Okay, it's very easy to fabricate long period grating because it's not very smaller periods are there. Periods size is going to be more in terms of the millimeter, not in micrometer. We did some modeling for that. We did some simulation for the long period grating. We'll show you all these results with you. But before going to see the result of the fiber long period grating, just to see some mathematical property of the long period grating. So the resonant coupling in the long period grating is totally depend upon the N effective. N effective here is totally depend upon the refractive index of core and cladding, because in the previous case only core, but here core and cladding, because in long period grating light signal is not going to be coupled with core modes only. Light signal is going to be coupled with clad mode also. That's why the clad refractive index play an important role for getting the Bragg reflectance. See this lambda LPG, this is the Bragg reflectance of the long period grating, and this is the period of the long period grating, and this N effective is the difference of core and cladding refractive index. So these parameters play an important role for the Bragg reflectance or transmittance. See here, this is how does LPFG work. You can see this is the optical fiber cable. This is region is the core region, and upper and bottom region is the clad region. Now here see your diffraction order is increased. It's now going to be -1. Of course, it is m is equal to 0 for the core, m -1 for the clad. Now see the light signal which is coming here and get reflected from the period and going inside the clad region, and then it will be going to be coupled with the clad modes, and then you will see the output. Okay, so here lambda, the Bragg wavelength will be N effective minus N effective 1 minus N effective 2, because both are the different wavelength with different modes. That's why it is minus here. In the previous case it was plus, because fiber break grating only more core modes are going to be coupled, but here core and clad mode is going to be coupled. That's why lambda is equal to N effective 1 minus N effective 2 and multiplied by period. And in this case the propagation characteristics beta 2 will be greater than 0. In the previous case it was not 0, but it is greater than 0. So if the light signal will follow this phenomena, then it will be phenomena of long period grating. Now see the output of the long period grating. This is the spectral response. You can see the particular range of the wavelength is going to be transmitted, particular is not going to be transmitted. C is less transmitted. So this is the wavelength typical transmission spectrum of the fiber break long period grating. This is the transmission, this is the wavelength. So you can see particular around 1600 nanometer, more very less transmission is there. So we can choose multiple transmissions of the signals according to the designing of the long period grating. One thing is here that the linear polarized mode is coupled with the cladding modes, and if linear polarized modes is going to be coupled with the cladding mode, then transmission spectrum is output will be like that. See, this is one of the paper which is very much useful in the research, published by the Wengsarker, author name the Wengsarker, A.M. Wengsarker, published in the Journal of Light Wave Technology. You can see concept is clear from this. See, this is the long period grating. Light signal is coming. Higher order diffraction will take place. Going in the clad region, coupling will take place, and then output will be like that. So this is your transmission loss. You can see this is for the fundamental modes, LP01 linear polarized fundamental. This is the losses of the different modes will be different losses will be there at the different wavelength, and that one we can calculate just by using the resonant coupling fundamental modes formula, and effective period LPFG is equal to lambda LPFG. This is the Bragg reflectance, transmittance, and this is depend upon the change of the refractive index of core and cladding region. Also in this figure you can see if the grating period is very less, around 150, see how the fundamental modes LP01, LP02 and LP03 is going to be transmission losses. See, transmission loss is if it is increasing the grating period, the fundamental mode loss is larger by increasing the grating period. So grating period play an important role. So here also there is a mathematical modeling we have did for the long period grating with core and clad modes. By just applying the couple mode theory, we make this equation, and using the couple mode theory, and this is the simulation result for the long period grating. So when you can see the transmittance for different length. Increasing the length, you can see the transmittance is going to be very sharper. See, now L is 1000 millimeter. How thinner, how sharper is the transmittance? So L play a very important role for giving the transmittance of the signal. Also, we have did some cascading of two LPG. We have combined two long period grating, and we got we did the mathematical modeling by using the couple mode theory, and we got the output like this. See, this is the two long period gratings combined together. Okay, and light signal is coming here. Then it's coupled with core and clad with the first LPG. See, it's going in the clad region, and then it's going again in the core region of the second LPG, and then coming output like that. So light couple into cladding by the first LPG is recoupled. See, here it's recoupled. All light is going to be recoupled here, recoupled, and with light propagating in the core, producing interference fringes, and that interference fringes will be something like that in terms of the transmittance you can see here. So this is one of the experiment which first time we did, cascading of two LPGs, transmission spectra of for the two LPGs which combined together, 5 LPG, 10 LPG, 20 LPG, you can see the transmission spectra, how is going to be very sharpened. Very easy, what we discussed in the previous, that just by using UV writing, one of the method for the writing of the LPG. Okay, and very easy, you can do in your lab also. You can just by symbol, just to purchase the UV writing source, and just purchase a fiber break grating, and you can design, you can write but you're supposed to have laser, you're supposed to be the OSA, and by using the UV writing, you can make your own grating inside your lab. So this is one of the way to making the permanent grating. So if you're writing the grating by UV, then it will be permanent. Also, we can make a grating which is reversible grating also. So there is also so many methods are there to make the reversible grating, to make the permanent grating. So I will not go so much deep on that. Just I will show you some of the method. Like this is the face mask technique. Already you are aware that when light signal is coming, this is a face mask, and the light signal will get interfere in the fiber core, and that interfere will change the refractive index. Okay, so this is one of the way. This is already you discussed about the UV writing, just point by point writing in the fiber. This is also the same way, because just here you are increasing the length of the period, and that length of the period you can increase just by increasing the distance only. So it's same method here. Here also one of the thing which is supposed to be aware that there is a photosensitivity of the fiber. Here you can see, we know that fiber is made from the silica dioxide, silica materials, and by using the light signal, we can disperse the atoms, and by dispersing of the atoms in the fiber, the refractive index is going to be changed. Suppose somewhere got more dense silica atoms, somewhere less silica atoms, so means there is change of the refractive index in the fiber, and this one will take place just by photosensitivity phenomena at 244 nanometer. Okay, so if you do photosensitivity phenomena at 244 UV light irradiation, then we can change the refractive index of the fiber, and changing the refractive index of fibers is not sufficient. Of course, the changing of the refractive index fiber in terms of the periodic variation, of the refractive index, then it's become a long period grating. So of course, precise method, precise distance movement is required for that. So here there is a comparative study of UV writing for LPFG using different laser. So you can see here the excimer laser have a wavelength is 157 nanometer, average power taking 12 milliwatt, and pulse duration, if you put 15 to 10 power f femtosecond, and exposure dose is around 5 joule is current density, and refractive index change, it will 5 into 10 to power minus 4. So different laser have different ability to change the refractive index of the core of the fiber optics cable. So multiple methods are there, multiple sources are there. Okay, so known photosensitive method is also there, just by using the carbon dioxide laser. You can see this is the physical deformation will take place inside the core region. This is the systematic figure where use the carbon dioxide laser source, and this is the fiber, and this fiber will move, and the carbon dioxide laser will change the physical deformation will take place inside the fiber, and we can analyze by the OSA from here. So these are the way how to make the long period grating. Also, you can see this is one of the very famous method, electric arc method. See, this is the fiber inside, and motor, precise monitoring motor is inside, and just electric pulse will be generated, and that electric pulse will be incident on the fiber core, and that electric pulse, or we can say arc current. Of course, there is a specific parameter. If arc current will be 8.5 to 10 milliampere, and electrode which are inside gap is 0.9 to 1 millimeter, and duration is 0.5 to 3 second, then periods first we can make is 15 to 100. So here the arc will incident in the core of the fiber, and by the motor it's moving precisely, is motorized, and then this electric arc current will responsible to change the refractive index of the core of the fiber. So this is known as one of the very famous electric arc by using the fusion splicer. Fusion splicer component, we can produce such type of the long period grating. Okay, so no need to go that. Here you can see that multiple methods are there for the modulation techniques. UV irradiations are there, near infrared femtoseconds are there. By using such type of the sources, we can, of course, there is advantage and disadvantage for each and every method. And first time did by the Wengsarker and some other scientists, but different the source, different advantage and disadvantage are there. So this is just all about different method to fabricate the fiber grating, long period grating. See, this is one of the very good method, reversible grating formation technique. Here, group's plate has been placed on the surface of the fiber, optical fiber. See, this is the groove plate, and a pressure has been applied. Pressure has been applied from the top of the groove plate. Then a periodic formation, or we can say periodic refractive index, will form inside the fiber. Also, you can see here another way that using groove plate. This is the fiber, optical fiber. This is the graphite rods, and just a pressure will applied. Then also you can see there is a deformation will take place in terms of the refractive index in the fiber. So these are the reversible. Once you remove the groove plate, then again it will come in the previous condition. So this is the reversible grating. Also you can see in this method winding of wire around the fiber. See, winding of wire around the fiber, tightly winding the wire on the surface of the fiber. Also it will be change the refractive index of the fiber. Okay, so these are irreversible grating formation techniques which are very much useful for the fabrication of the long period grating. A lot of applications we have for the long period grating as well. Already we discussed about the optical add drop multiplexers. Just we replace with this multiplexer with fiber grating, long period grating, and according to design of the grating, we can add and drop the signal which is multiplexed together. Same thing is here. You can see here, this is the grating periods inside, grating periods, area of the long period grating. Multiple input signal is coming here. Multiple input signal is coming here like a multiplexer. This is a circulator 1, circulator 2, and this is area of the long period grating. So you see, multiple signals are coming here, but suppose you design a grating who is matching with a wavelength any of one. So what will happen? That well, maybe it's going to be reflected back, and which is not designed, then it will be transmitted further. So it's depend upon the grating size, grating period, which one signal you want to add, which signal you want to be drop out. So this is one of the very good application of the long period grating in the DWDM system. Very much useful for the sensing technology. See, long period grating is much more preferred compared to the fiber break grating, because see here, this is the working principle of the fiber break grating. This is the working principle. How does it work in the long period grating? In the FBG, all the modes couple will take place inside the core only. But in a long period grating, you can see light signal is coming and it's going in the clad region. So if any sensing substrate, see here, sensing substance is here, is a sensing substance, and light is coming from here. So sensing substance will get more attraction, more collapse with the cladding modes here, and that's why the higher the sensitivity here will be larger. Because the substance will come in the contact with a cladding modes or evanescent field, we can say, and that's why after a lot of interaction will take place with light modes, light particles with the substance which are using for the sensing purpose, and then it's going outside. And here we can see more accurate, more sensitivity will be there if you use long period fiber grating for the sensing purpose. This is one of the application of long period grating. So it's very simple, very easy to fabricate. These are the way it's motivated us to go for such type of the grating. Okay, so just okay. So now we did some very easy way to fabricate the long period grating. You see, this first time we fabricate the groove plate. See, different size with 600 micrometer, with 1200 micrometer, 1800 micrometer, and 2400 micrometer. First time we make this type of the groove plate, and this one placed on the surface of the fiber just by pressure, and we got a fiber break grating, long period fiber break grating. This is another way to make fiber break grating just by using the splicer machine. You can see how does fiber cladding has been removed, then sleeves will be inserted inside, okay, and one end will be inserted one side, other end has been inserted from the other side, and then close this splicer machine, and then fiber is going to be combined, and just move the some of the move the that particular point, and again do the same thing. So what will happen? Multiple combinations, multiple changing of the refractive index, like a period will take place inside the fiber. So this is one of the way how to by using the splicing machine fabricate the long period grating. See, this is the splicing machine, and this is the way, just by removing the claddings and by so many methods, just you put the fiber from one end, and the same thing you can do from the other end, and then close this, and then it's become change of the refractive index in that particular place. So this is one of the easier way to fabricate the long period grating. And after putting the pressure, we can see what are the results that take place in terms of the transmission spectrum of such type of the long period grating. So this is the transmission spectrum of the long period grating. See, this is the whatever different periods, we got different resonance wavelength. See here, and this is for the 600 micrometer period in the single mode fiber. So you can see that resonance wavelength is different at 1466, at 1510. These are the resonance wavelength of 600 micrometer period for the single mode. Same thing we can do for the other. See here, this is the transmission characteristics showing for the 600 micrometer. Here combination of again multiple fibers. See, multi-mode fiber is a single mode fiber, this is the multi-mode fiber, and this single mode fiber have two grating. One is long period grating, one is ultra long period grating. Just to increase the size of the periods, now become ultra long period grating. So if you combine these two gratings, and here use the multi-mode fiber, because we know that multi-mode fiber easy to combine, because the core and clad the diameter is larger, is 62.5 125 with the multi-mode fiber, and here also other end also we use the multi-mode fiber, and this is a single mode fiber. So it's easy to splicing up this long period grating with the multi-mode fiber. So if it is like that configuration, and if suppose light will coming here, see, from the broadband source, now so light will enter inside the grating, you know, in the grating, the property of the long period grating is what will happen? There is coupling will take place going in the clad region. Modes are going in the clad region, and then again couple back and going in the multi-mode fiber. And here you can see in the OSHA what are the coupling will take place, what are the transmission characteristics or reflectance characteristics, whatever it is, we can check from the OSHA. So different configuration, different output we can see. Here you can see that complete spectrum of long period grating and ultra long period in single mode fiber. How does resonance peaks are there for the different periods, size 600, 1800 combined in the same figure. You can see that 1800 micrometer period, your resonance wavelength, it is more coming at 1570 nanometer. But if 600, then resonance peak is coming around 1610. So different periods, size, different resonance wavelength. So as I told, according to our requirement, we can make the grating period and we can get the resonance peak. So 600, it is the resonance peak at these three wavelengths: 1466, 1510, 1595, and at 1200 it is 1475, 12, 1521. So different peak we are getting, resonance peak we are getting at different period. This is the conclusion of our work. So this is the same thing is here for the different periods. You are able to see different power. This is the transmission characteristics for the different. See here. Here we are using the long period, it is 600 micrometer, but different weight. See, if your weight you are putting from 3.87 kg to 2 kg, see, putting the weight on the long period grating. Okay, so different weight, different peak you are able to see. So how come the weight will affect the transmission characteristics of the fiber? You can see here. Of course, we are getting the same peak for all, but of course some peak have the very deep. Some, if the weight will increase, then peak will very deep, and weight will decrease, then peak is very less. Okay, so this is the transmission spectrum of the light signal for the long period grating with different weight. Here showing the transmission loss with respect to the weight. So if you are increasing the weight, transmission loss will take place. Increasing the weight, see, or we can say equivalent applied pressure. So pressure will apply, your transmission loss will take place, or we can say bandwidth is going to be decreased. Okay, so this is just transmission losses and resonance wavelength for the applied pressure for the ultra long period grating. When period is around 1200 micrometer, you can see period has been increased very big. Now it's become ultra long period grating. So different ultra long periods, different losses will take place with respect to the weight. So same results are here. Just how does weight will affect the transmission characteristics. Here the different periods, powers, different peak of the different resonant peak, different Bragg reflectance, we can say, Bragg transmittance, we can say. Okay, so these are the property. Now we will see some of the application of the long period grating. So the MSM, when we combine the multi-mode fiber, single mode fiber, multi-mode fiber, then this is the property of MSM, long period fiber Bragg grating, which is not only to see about transmittance, not only to see about the transmission loss, also it's very much useful for the band reject filter. See, this is another application of the long period grating. You can see this range, this is your full width maximum height, and it is around 15 nanometer. This yellow color you can see, this is yellow color. With and without grating, you can see what are the power loss will take place. Also we can, and this range is going to be reflected back, or we can say this range is going to be filter out. Okay, so this is another property of the long period grating, work as a filter. Same thing is here, different gratings has been combined together, and we got the different output in that way. Okay, so one of the very good application of the long period grating is fuel adulteration detection. Fuel adulteration. So fuel adulteration, excuse me. Fuel adulteration by kerosene is one of the serious issue. It will increase the pollution. It will decrease the engine performance also. So how to detect that one? We can detect this very easily just by using long period grating. Can easily detect just by long period grating. You can see this is the systematic experiment. Broadband laser source, fuel will in, and going to be combined, or we can say LPFG means what? Light signal which is coming from here, it's going to be the clade region, and that clade region modes is going to be interact with fuel components, and that fuel components once will combine together, interact together, and what is the sensitivity of that we can get from the optical spectrum analyzer. See here, this is the transmission characteristics of long period grating for different percentage of kerosene in petrol. You can see once it is air, then your graph is in terms of normalized power and wavelength is like that. But if you increase the kerosene around 30%, see, you're going to see the is your peak very see, it's going to be around 1550 nanometer. So more mixture of the kerosene in the petrol, more is going to bend towards the wavelength. Normalized power is going to be reduced. So for the 30%, for 20%, for 10%, you can see the figure, and this is the one of the way to detect the fuel adulteration. Okay, so next one is apodized grating. We can make just by applying the pressure, and we can see in optical spectrum analyzer, and the output for the such type of the grating, it will be something like that. You can see for the uniform grating, for the apodized grating, you are able to see the same output but different in peak, different in okay. So these are for this another 1200 nanometer. This is for the another shape. Another is the chirping. Chirping is also one of the important grating. Chirping means just modulating, or we can say modulating the grating size. See here, grating size how is modulating, 17 millimeter, 9 millimeter. So if you make a grating in this way, if you design a grating in this such type of the length, then it's known as chirp grating. And for that, the application of course is different. Is very much useful for such type of the grating. See, this is the transmittance for the chirp effect for the 600 micrometer. For uniform grating, you can see blue color, and chirp grating you can see the red color. How the shifting towards the longer wavelength. Okay, so these are the okay. So these are the different way to fabricate the grating just by fiber deformation, single side, double side loaded. See, single side loaded, double side loaded, different way to make the different type of the grating just by applying the experimental setup for the double side loading, applied the pressure and the fiber, how the broadband after that apply the broadband light source, how does you can see the optical spectrum analyzer. So these are the way how to fabricate the long period grating, a different method. Okay, these are the output of the multiple grating. Okay, these are the output. These are the cascading of the multiple fiber. Okay, so we have taken so many reference for explaining all this. Okay, so from that I would like to conclude. Now, if anybody have any questions, if anybody have anything, you can discuss. Thank you very much. Thank you. If anybody is interested to work in long period grating, fiber break grating, how to fabricate, what are the method to fabricate, and how to do the simulation, and how to use the transfer matrix method, couple mode theory. If anybody have any such type of the interest, anytime you can contact me. I will be happy to answer all of your question. My email ID is with sir. You can mail me. Yeah. Yeah. Thank you. Thank you
Any
very much.
question from the participant side? Any question?
Sir, I put my question in the chat box. Please see. Can we use the fiber Bragg grating as a oxygen level sensor for the human body?
Of course, yes. There is a lot of possibility because see, it's very precise. We are talking in a nano in scale. If you're talking about the fiber break rating, so we are talking in nano in scale, in micro in scale. So and the output of fiber break rating, we are getting in terms of the reflectivity. So the reflectivity wavelength, it will be shift if there is any change in the patient. If there is a change in terms of any disease, suppose anybody is suffering from dengue fever, so that reflectivities of substance will be different compared of the person who is not suffering from the dengue fever. So based on the shift of the wavelength, we are able to know what are the problems is happening to any patient. It's one of the way to a lot of use nowadays in health monitoring. Fiber break grating not only for the breathing purpose, just also for the any surgery which is very much precise, especially in the brain, and you see one of the very big problem is the stone inside that stone. How to detect if it's nano in scale? That one only we can do just by optical fiber sensor. So these sensors are very much useful not only in the health but also in the optical communication system.
So, how to decide whether we should use LP, FBG, or the reflectivity fiber Bragg grating?
It's depend.
Depending upon the okay, yes.
It depend upon the size what you are planning. If you want to be measure which is in millimeter in scale, in micrometer, then of course you go for the long period grating. But very smaller in micrometer, in 10 micrometer, less than 10 micrometer, then we can use for the fiber break grating.
Thank you very much, sir. Thank you.
You're welcome. Yeah.
Good morning to our most valued invited guest and learned speaker, Professor Vivekanand Mishra, Alliance University, Bangalore, and all. I, Pushpen Kumar Gupta, Assistant Professor in Electronics Engineering Department, on behalf of the Institute I.E.R.T. Prayagraj and the entire team of this Atal Fdp, and on my own behalf, extend a very hearty vote of thanks to Professor Vivekanand Mishra for your important work and sharing with us your findings today. Design formation and characterization of optical fiber gratings is very interesting topic. This fruitful, informative session covers many fundamental and advanced things related to design formation and characterization of optical fiber gratings. I hope this session must be helpful to all the participants to improve their research quality and teaching skills. Once again, thank you so much for giving your valuable time and such a nice eye-opening session. Thank you, sir.
Thank you, sir. Thank you very much. Thank you for giving me such opportunity. In fact, I have so many other things to introduce with all the participants, but due to the time limitations, I'm not able
Yeah,
to
yeah,
do.
sir. I saw in the
Yeah,
PPT
if we get
also.
time in future, we'll interact again with all the participants and all.
Okay, sir. Thank you, sir.
Thank you very much. Thank you. Thank you.
Thank you, sir. Okay. Again, from 11:30, we are going to have the next session. Hello. From 11:30, we are going to have the next session by Professor Bijesh Kumar sir from MUT Gorakhpur. And it is going to be on the organic semiconductors, and in inorganic semiconductors, he's going to discuss about the design issues and its characterizations about the semiconductors, inorganic and organic semiconductors, and its device modeling and its design issues, its characterization issues. So please be at 11:30